Let me check in the back of the book. See what we got. 19 point part C is 1.4 times 10 to the minus 7 joules. All right, so there's that. Let me see how I'm doing on time at the moment. We still got plenty of time. All right. So I think next up here, we will work a problem with letters. Oh, I hope I got that in the last video. Oh, man. Well, yeah, we'll see. I really hope the conclusion to that last example was in the previous video, otherwise it's annoying. All right, anyway, moving on here. Let us do another example. And so I think I'm going to step away from the book problems for now. I think we've worked some good problems. I may pull a problem example out of my lecture notes next. But before I do that, I thought it would be good for me to work the find the voltage function for a cylindrical, like for a spherical shell kind of problem. So suppose you've got a charge Q, uniformly distributed, right? And we have inner radius A, outer radius B, right? We worked out the electric field in this kind of situation, right? And here it's empty, in the middle. So the charge is distributed over this spherical shell, solid shell, all right? And so what we did was we said, okay, well, inside here, right, if I put a little Gaussian sphere inside, if I have R less than A, we get Q enclosed is equal to 0, which by the spherical symmetry implies that the electric field at such radii are 0, right? So this is for 0 less than or equal to R less than or equal to A, all right? No charge is enclosed in that situation. But then if we put the Gaussian sphere out here, right? So that's case 1. Case 2, if we have A less than or equal to R less than or equal to B, we get that the charge enclosed by such a thing is equal to the ratio of the, all right, so like the volume that we have enclosed is 4/3 pi R cubed minus A cubed. That's the volume that there's charge. Now the whole charge is distributed over 4/3 pi B cubed minus A cubed. We talked about this a few times in class, I think. That's the ratio of the volume that's subtended by that Gaussian sphere. So I multiply by Q, and that gives me the charge enclosed inside my Gaussian sphere there. And of course, then I apply Gauss's law. Just to review, to recap, Q enclosed divided by epsilon naught is equal to, 4 pi R squared times E, because we have got spherical symmetry. That's the flux. And so lo and behold, we get the formula that the electric field is equal to, let's see here, Q times R cubed minus A cubed divided by 4 pi epsilon naught R squared times B cubed minus A cubed. All right, great. And that's for A less than or equal to R less than or equal to B. Great. That's my electric field in that case. And then, of course, there is one remaining case, case 3, we could be out here for our Gaussian sphere. In that case, it's easier. There's not much calculation to do here. And 3, we just get Q enclosed is equal to the net charge Q, and then by the usual calculation, we get 1 over 4 pi epsilon naught. 1 over 4 pi epsilon naught times Q over r squared, right? We get the Coulomb field when we're outside, where the charge is distributed, and that's for, all right, so that's for r greater than or equal to b. That formula drops back to the third formula in that case that r equals to b. You get the cancellation of the b cubed minus a cubed, and it leads you back to q over 4 pi epsilon naught b squared there. Great. Now, so then to find the voltage, since this field is purely radial in the spherical direction, to find the voltage we merely have to integrate with respect to the radius, which is not too bad. Well, yeah. So in all cases, you see that the electric field is minus dV dr. So how do you integrate? How do you integrate for voltage if the electric field is defined case-wise? Well, you have to integrate case-wise, right? So like the voltage, I'll try to do it all at once. The voltage as a function of r is going to have 3 cases. So the middle one is the easiest. What's the integral? dV dr equal to 0 is constant, right? So I could call that, for lack of imagination, I'll call that constant V naught. That's for, 0 less than or equal to r less than or equal to a, all right? And then if I integrate the other case, this one down here, of course I'll get q over 4 pi epsilon naught r, and that's going to be for r greater than or equal to b. Now, I have to add plus a constant, let's call it v3. All right, that's going to be, I'll call that, well, I guess if I'm calling that, let me call this one v1. So I got v1 for the first case, v3 for the third case, and I'll put a constant of v2 in the middle case. If I integrate, how does this integrate? Right? How does that integrate? Well, it's kind of scary looking, but let's break it into pieces that we can handle. So what's going on here, if we break this into 2 pieces, it's probably easier to integrate. So we've got electric field is Q over 4 pi epsilon naught, and then I've got r cubed upstairs, I've got r squared downstairs, and I've got b cubed minus a cubed. So that's my first term. And then I've got minus qa cubed divided by 4 pi and epsilon naught, your little r squared, the difference of b cubed minus a cubed. All right, great. These are really different in terms of how to integrate, And all right, so let me rewrite this a bit. So what we've got is the electric field is, let's just call it a constant. Let's call it gamma times r. All right, where gamma is actually q divided by 4 pi epsilon naught, the difference of the cubes of b and a. And then over here, I've got minus, let us say, beta divided by r squared, all right? And again here, gamma is simply q over 4 pi epsilon naught, difference of the cubes. And here beta is q over 4 pi epsilon naught, difference of the cubes. Wait a minute, could I use the same? Oh man, dudes. Well, that was dumb. I don't need an alpha. I don't need a beta and a gamma. I could use gamma for both. It's the same constant. Why didn't I just factor that constant out? For shame. For shame. All right, let me fix it. This is, good grief. gamma times R minus phooey, they are different. It's that time of day. Q minus beta divided by R squared. All right, so there's a slight difference because this one's got the Q and the denominator. This one's got QA cubed. The beta's got the QA cubed. That's what I'm missing. There's a difference. This one's got A cubed. Anyway, beta is just equal to A cubed times gamma, for what it's worth. I don't know. There's a law of diminishing returns here. But the point is, I just wanted to reduce the baggage so I could see the integral. If I want to integrate this, and so like the voltage is minus the integral of gamma R minus beta over R squared dr, okay? Because I need to integrate to find the voltage. So I get, minus gamma R squared over 2 from the first term, and then I get a, golly, sorry, I'm not functioning well here. So the integral of minus gamma R plus beta over R squared dr. I feel like it's bugging me. Oh, I guess it's okay. Yeah, that is what it is. All right. So when I integrate that, I get minus 1/2 gamma R squared, and I get a minus beta over R. It was bugging me that I get a minus there, but it is what it is. Okay, so minus beta divided by R, and that's plus some constant, which I'm going to call V2. And this is for A less than or equal to R less than or equal to B. All right. So the voltage doesn't have three, constants in it that are just willy-nilly unrelated. Because there is no concentration of charge at the interfaces here in our problem, as we're assuming, we know that the voltage has to be continuous in the transition between these regions. So I can make some choices here, right? Like I can say, okay, I want my voltage to be 0 at infinity. So if I choose that, right? If I choose the voltage to be 0 at infinity, then we can make progress on this, right? So like if V of infinity is equal to 0, then that makes us give V3. We set V3 to be 0, right? So V3 would be 0. And then what? Well, let me pan over here so you can see what I'm doing. So then we need to make the third case and the second case glue together nicely, all right? So I think we can see everything. There we go. So to put those together nicely, I need that, like, the case 3 and the case 2 match up, you know? At R, we need to look at R equals to B. So at R equals to B, we'll have Q over 4 pi epsilon naught B from the Coulomb potential on the outside. And that's going to have to be equal to, I'll use my stupid gammas and stuff for a second here. So minus gamma B squared divided by 2. Minus beta over B plus the constant V2 we're trying to figure out right now, because we're trying to figure out what constant we have to add in case 2 to make it continuously match case 1. All right, case 3 rather. All right, so let me solve this, this gives us V2 is equal to, Q over 4 pi epsilon naught B, and then minus, not my gamma, let me put it in, it is Q over 4 pi epsilon naught difference of the cubes, Q over 4 pi epsilon naught B cubed minus A cubed, right? That's my gamma. But then I'm still multiplying by minus, and then we've got a B squared over 2, right? I'll put the 2 up here so I can see it. All right? And then I've got minus beta, and the beta is, oh, excuse me, I'm solving for V2. So when I put it on the other side, this minus becomes a plus, and this minus becomes a plus. But my beta was QA cubed divided by 4 pi epsilon naught difference of B cubed and A cubed. All right? And I'm still dividing by B, so I've got a B down here. All right? And if I haven't missed a letter or done something stupid, then that should be V2. Now I think we can clean this up a bit, and let's do that. So V2 should be equal to, we'll factor out a Q over 4 pi epsilon naught since we can, and then we're up against a 1 over B from this, plus, let's see here, we got ourselves, B squared over 2 plus, I guess, A cubed over B divided by B cubed minus A cubed. So, man, this is it's a funny formula. So that's the voltage. I'd have to make the voltage constant in the middle case to be that in order to match up with the Coulomb potential. Right? So there's that. And then finally, what's V1? So there I would look at R equals to A. Right? I'd look at R equals to A because there I have to have the voltage functions match up there as well. And we should work some problems where we have charge on the boundary so we can have a jump in the voltage. Maybe I'll do that next example of that. But anyway, so R equals to A, we've got this mess. This horrible formula. So where did my voltage formula go? Here it is. This mess. So we've got, golly. Well, anyway, it's pretty simple. We have V1, that's the inside voltage, right, is equal to, a minus gamma A squared over 2 minus beta divided by A, because that's R in this case, plus V2, where V2 is this monstrosity, And then, of course, we could work this out. I could actually put in my gamma and my beta. So like V1 would be. I'm done. I hope you understand the point here. I mean, and I wouldn't be terribly surprised if I put one of these in the homework or something. And you'll do better on paper than I'm going to do on the board right now because it's the. Anyway, I'm tired, so I'm going to stop here. I think I've showed enough that you can see what you're doing. We just have to put it in. You probably could make a common denominator here, and maybe stuff nice happens. I don't know. It's very possible. But if you wanted to know what the voltage was in the middle of the sphere, though, in the case we put the voltage to be 0 at infinity, this is what you have to work through. So, it is what it is. Okay, so let me see if I can find an example for us to look at in the notes. And I think I was supposed to go over the solution to test 1 in here too, so I probably should do that. That should be easy enough to do. All right, there we go. See the projector come down. See if I can find a problem in the book that had the issue I was just talking about. Well, 28 looks interesting, but it's even, so I'd kind of like something I could check. Well, that's I'm trying to find something with a I don't find the problem I want. Well, 39 might work, actually. I'll try to do 39 here in a second. But first, let me show you an example from the notes, since I already got this thing out. Let's see if I can find it. All right, so physics, we are in potential. And here, I'll plug us in. Turn off the lights. I might fall asleep though, it's not good. That should be okay. See if I can make this bigger. Is there no full screen option? Well, that's not helpful. Fit the page, I guess that'll have to do. Is there no full present maybe? I guess that'll work. So we worked through some of this stuff before. Let's see here. I mean, I didn't do everything in here, but I think I've explained the ideas. We did part of this today. This is the other thing I was talking about, but I didn't actually put on the board. Come on, it won't let me. Well, that's annoying. Ooh, well, that's interesting. I broke it. Huh. Come on. There we go. So this is one of the things we should talk about briefly before I forget. So suppose I was trying to understand things about the voltage of a half circle with charge q spread uniformly, as pictured there on x equal to 0 and y squared plus z squared equal to a squared. At some point, all right, x0, 0, right, find the potential. I mean, I can do that. I can find the potential, see, because it would be, the thing is, all of these points are the same distance from there, right? So fine, I can calculate that the voltage at that point, right? The voltage at that point is given by this formula. That's true, but the rub is that formula does not capture the dependence of the voltage at nearby points. You see, so the only that's a problem, right? Because this makes it look like if you took the gradient of the formula, you would just get an electric field which points in the x direction, right? But that's obviously not the case, right? Because like if the charge is up here, the electric field's going to be pointing down like that a bit, right? It's going to be down. It's not just going to be purely in the x direction. It's going to point down below the xy plane, right? And and by the symmetry, it's going to have a y component of 0. And we're not. You don't see that if you were just to naively take the gradient of this, you'd be misled, because this formula is only valid at that point. It's not valid at points nearby that point. And so what I'm trying to say is the calculation we did today in the other example is very much based on the symmetry in play. And if you don't have that symmetry, you have to do a more sophisticated calculation, which I've not done here. To do the sophisticated calculation, I would have to consider, like I would have to put x, y, z here and actually do the integration like that. And it wouldn't be as easy as this. So, yeah. But I do think I can understand. This is enough to figure out the x partial derivative, because this does capture how the voltage varies. If I was to slide up and down the x-axis there, I do have that much information from the setup, so I can figure out the x component of the electric field by differentiating with respect to x. But I cannot conclude, like I said, that partial v partial z is 0. You can see that physically. The mathematics of it is just that I've not explored how the voltage. I've not captured in the variability of the voltage if z is not equal to 0. So the best analogy I can make is it's kind of like a problem in Calculus 1 where you've got a related rates problem and you're putting in the constraint before you differentiate, and then you differentiate and everything's 0. It's like, oh wow, I guess it's 0. Well, no, you just differentiated after you put in constraints, and you can't do that in that context. And something similar is true here. So we worked through this in a slightly different notation, but we worked through this. And I worked through this a previous day, right? The voltage for the uniformly charged sphere, and I tried to just show you how we would do the spherical shell just now. So here's another example that I have in the notes that's worth spending a couple minutes talking about. Example 38, I have y is equal to y naught plus 3t squared for a particle with mass 1 kilogram and charge of a convenient charge, a charge which just happens to cancel the the constant k, 1 over 10 times 10 to the 9th coulombs. Suppose y is the vertical direction. We do consider gravity. If the only other force acting on m is the electric force due to the pictured plane charge, which is a conductor this time, then what's the surface charge on the plane? So here's what's going on. We got this mass. It's got electric force QE going up. It's got gravity m minus mg that away, right? Mg that away. And we're told that the equation of motion for the mass is this, which tells us implicitly that the acceleration must be, acceleration divided by 2 has to be equal to that 3 if you think about the calculus here. So we have ma, come on, equal to QE minus mg, because the forces at play are the electric force and gravity. All right. So all this together means that m d squared y dt squared is equal to, and the electric field is sigma over epsilon naught, remember, because it's a conducting plane, so that means that sigma over epsilon naught's the charge density there. And of course I can calculate the acceleration and I get 6. This is acceleration, right? All right. And I'm supposing that there are implicit units in there because, yeah. And then if I solve, so I've got m times, apparently, was it 6? Is that right? Oh yeah, 6, duh. I said it had to be half. That has to be acceleration over 2, so it has to be 6, great. So anyway, solving m times 6 equals to all this for sigma gives me the formula down here. And what is it? Well, come on, computer. My computer is getting dumber every day, a little bit dumber. And yeah, so you plug in those numbers and end up with 1.26 coulombs per meter squared, which is a lot actually. And so there you go, that's our charge per unit area. So what's this? I've not written notes about electric field equal to 0. Read in the book. Yeah, the book does have a nice discussion of how to think about voltage inside a conductor. And so in a nutshell, the voltage inside a conductor has to be constant, because if it wasn't constant, that would mean that the gradient is non-zero. And if the gradient was non-zero inside a conductor, that would mean that there's an electric field inside the conductor, which would mean that the electric charges are moving inside the conductor, which would be problematic because we're in electrostatics, and we know that after a short amount of time, all of the charge has to accumulate to the boundary surfaces of the conductor in this electrostatic situation. So we have to have constant voltage inside a conductor, which is probably the key to working the next problem here. But while I've got the projector out, let's talk about the test. So if I can find it. I hope I saved it. That would be annoying if I haven't saved it here yet. Wouldn't be terribly surprising though. Let's see here. Well, oh, here it is. Woohoo. All right. So I'll try to be brief. Problem 1, we had calculate the magnitude of the electric force between two electrons. So we simply use, basically kQq over r squared, which is also known as 1 over 4 pi epsilon naught. Electron charge times electron charge divided by the distance between them squared, which is 0.094. And you crunch the numbers, you get 2.611 times 10 to the minus 26 newtons. This one here, thick conducting slab, surface charge density sigma, my back, causes a 3 kilogram mass to float above the slab, which means that the electric force and gravity, they must be balancing, otherwise we would have non-zero acceleration and not floating. Since I haven't given you any other kinematical data, you must assume it's at rest, all right? Like that's the only reasonable interpretation of this problem. So I'm telling you the mass has a 44 nanocoulomb charge, and asking what's the value of the charge per unit area on the conducting slab. So my E here is sigma over epsilon naught, the Q is given, and so I just solve this for sigma and crunch the numbers and I get that. So some of you put, like sigma over 2, but that wouldn't be appropriate here because it's a conducting slab, so all of the flux goes above the conductor. Problem 3 is just a plain old Gauss law problem, and symmetry is involved. I tell you the charge is at the middle of the cube, which means that 1/6 of the flux must go through each of the faces, but the net flux is the charge enclosed divided by epsilon naught. So on the other hand, since the flux through each face is the same, 6 times the flux on the given face is the total flux, which is 750 Newton meters squared per coulomb, which when I solve for Q, upon multiplying that by epsilon naught, I get 6.41 nanocoulombs, like so. Problem 4, a lot of you guys got. It's actually not hard once you understand how to set up the formulas, and it's really just need to look at the displacement vector between the field point XYZ and the source point, which in this case is L2L 3L. And so this is the displacement vector between the source point and the field point, and I divide by the length of that vector cubed this gives me, this is basically just a nice way to write the formula r hat, well, this over here. You know, a lot of times you'll see the formula r hat divided by r squared, but you know, who wants to write? All that does is put a square root over here, and you have to write this twice. Why not just write it once? This is the easier way to write the formula. So I'm trying to make it easier on you guys, and many of you did do that, so it's good. It's good. This problem actually was on my first test in Physics 2 undergraduate with, I think, different numbers, but pretty much the same problem. That's where I got this problem, point in personal history. But anyway, Q1, you know, Q2 are as pictured. They're placed at the corners of this, you know, square. And you're given the side length is 50 centimeters. And you're supposed to find the electric field at A in terms of both magnitude and standard angle, and then also B, if a minus 3 nanocoulomb charge is placed at A, what's the force, magnitude, and standard angle. So I find the electric field from 1 is leftward because Q1 is a negative charge, which makes the electric field go towards it. So that's why I have minus K magnitude of Q1 over L squared. And I put magnitude there just because I said Q1 was negative, but I already put the minus over, I don't know, just I do better sometimes by putting the minus there and thinking about the magnitude of Q1 rather than Q1 being negative, but whatever. I hope you get what I'm at. It's probably because I didn't want to white something out. I don't know. It's kind of weird the way I've written it, but whatever. It's not wrong. It's just weird a little bit. Anyway, so E2 on the other hand is vertical because Q2 is positive, which means its electric field's going away, which puts it upward. And so you got a horizontal and a vertical field, and you can add those as I did. Factor out the K over L squared because you can. I let L equal 0.5 meters, so I don't have to keep writing that everywhere. And my K divided by L squared, and then, so here's my minus 2 nanocoulombs and my plus 3 nanocoulombs. But I put all the units out here in the newtons per coulomb, and anyway, I get this. So that's the direction of the electric field, which is like negative for X and positive for Y. That puts it in quadrant 2, which is where you have to think through the standard angle, folks. A lot of you are still being careless about standard angle, which is unfortunate because you lost points again about that. And you will continue to lose points about that until you learn how to calculate standard angle carefully. It's something we can all do and we should all do. Anyway, so I have to subtract that inverse tangent from this to get an angle which is between 90 and 180, which is where it should be because of where it is geometrically. It's in quadrant 2, right? So 123.7 is what I got. And the electric field's 129.7 newtons per coulomb. The force is the charge times the electric field. But since the charge is negative, it reverses the direction from, it's not the same direction because it's minus charge. So it flips it over, and so you get this magnitude, and it's directly polar opposite direction-wise. So you go over, I really should have a picture. Oh well, I'm sorry. Minus 56, or if you like 303.7 degrees, which I think should be, if you take 123 plus 180, that's what you get. Problem 6 should be a gift. We derived this in class. This is a standard, important example in the material. Many of you were not prepared for this. That's unfortunate because we should all get this problem. It's standard. We take a Gaussian cylinder, we surround the line charge, and we calculate the flux through that. It has to be radially outward because the line charge is like that, and anything else would violate the symmetry of the line being very long. So the flux is just the surface area of the side, which is 2 pi RL, and then times E, that gives me the flux. The charge enclosed is the charge per unit length times the length. So of course these L's cancel. We should always have any kind of characteristic distance of your Gaussian surface. They must cancel out in the derivation. There shouldn't be an artifact, like there should not be a, you shouldn't have some sort of like dimension of your Gaussian surface which is not what's the word? Like the L is totally artificial. It has nothing to do with the actual magnitude of the electric field. Like that should be intuitively somewhat clear from this, is like the magnitude of the electric field is just about the radial direction here, just from the symmetry. And L shouldn't figure into the formula for the E. It really shouldn't. And so a lot of you had that still floating around in your answer, which is not, means something went wrong. Yeah, so anyway, do the math, you get lambda over 2 pi epsilon naught r, and that's the formula for the electric field of a very long line charge, which we have seen a few times now. Then, let's see here, that was problem 6, I think it was. Okay, so problem 7, imagine a uniform charge Q distributed over a spherical shell from r equals a to r equals to b, and also we added a point charge at the origin just to make it a little bit different. And so essentially, I asked you what the electric field was inside, just in one case, inside the charge, the smeared out charge. And so I'd make a Gaussian sphere there. And of course, I am enclosing the fraction of the charge that's in the shell, just like I did earlier in the problem session. So there's that lovely formula again. Bop. But also we have the Q at the middle. So we have that plus that charge is the charge enclosed. And so the electric field is thus this. All there is to it. But obviously not everybody got that one. And you know, it's a moderately difficult one for this course, so it's, you know, but I think everybody has a shot at it if I was to ask it or something like it again. I warned you guys, integration matters, and true to my word, integration does matter. There will be integration. This is a calculus-based physics course, so there's supposed to be calculus on the test. In any event here, so to find the electric field due to a line charge, we find a little bit of electric field that comes from a little bit of charge there, and then we simply add those up by integration, which is the continuous sum. And so I work it out. I've got k dq over x minus 2l squared there, but I found making a u substitution helpful, and after a bit of calculus, I end up with k beta log of 1/2 plus 1, and at least one person got this answer or something like it. Maybe a couple of you. Some of you at least started right, I think. But anyway, don't count yourself out for that. You do need to learn it if you haven't learned it yet. Okay, so next up here, this one is the another question about a conductor. And so I just put what did I do? I put a positive charge, a uniform positive charge on the middle, the inner solid sphere of radius A, and then I had a conducting spherical shell outside it with A less than B less than C. If the net charge on the conducting shell is 41 Q1, then find charge at radius C. So part A, since the electric field is inside the conductor 0, it must be that the net flux is 0 going through a Gaussian sphere that was like in here, you know. So the charge enclosed must be 0 thus, but that means that QB has to be equal to minus Q1. But we also know that the sum of the charge that's at radius B and at radius C has to be 41Q. So that tells me that the charge at C is 42Q1. So yeah, there it is. Now for part B, the electric field from 0 to A, this is a standard calculation. This is like just the uniformly charged sphere, and we find that the electric field is linear from the middle, and it goes to the Coulomb potential, the Coulomb field at the surface. But again, Gauss's law on the sphere inside here. This is the charge enclosed. It's the volume inside this Gaussian sphere divided by the total volume times the charge that's on the inner sphere, which was Q1. And then C, what's the electric field for B less than C? That's an easy one. Everybody should have got that. 0. The electric field 0. It's inside a conductor, right? Don't have to even think about that one. That one's just a gift. It was a gift that not everyone freely took, though. Not everyone was willing to accept my gift, but maybe next time. So, and then the electric field for R greater than C, outside, once we're outside everything, it's the Coulomb field with the net charge, whatever that happens to be. I guess it was 42? Is that right? Yeah, 42 Q1 over 4 pi epsilon naught, radially outward. So there's that. And then this last problem was a bonus problem, but I don't remember if anybody, I can't remember if anybody got it or not. I hinted at this possibility during the review session. I mentioned that, MA can be written as M VdVdx, and maybe you could solve it because, you learn separation of variables in calculus 2, so you can work it out. And so here we have MA is equal to the electric force, which is QE, but for the line charge, as you derived earlier in the test, some of you, Q over 2 pi epsilon naught x, because x is R here. So that's my electric field. And separate and integrate, and that will get you the velocity as a function of distance. And so I do that, and lo and behold, I get this lovely formula. Woohoo! So yeah, that was your test. And so some of you survived, and some of you thrived, and some of you are waiting for the final. And that's okay. I mean, it happens. It's not what you know in the middle of the course that matters to me so much. It's what you know when you leave the course. And so if you can remedy whatever it is that you've missed up to this point before the end of the semester, then that's fine by me. I will not necessarily judge you by one bad day in here. Now, if you have another bad day on the final, I'm sorry, but at some point, you have to solve stuff. I can't just, go off. I don't know. What else would I go off of? I mean, we're not allowed to take bribes, so I can't do that. And, well, I wouldn't do that anyway, but even if I wanted to, we're not supposed to. What else could there be? I mean, I could, some sort of, I mean, there's just not, I mean, you have to show that you can do the material, right? That's ultimately what it's about. So there is no way around that. At some point you have to learn it. And so if you haven't done it yet, then do it later in the semester, and there's still hope. So I think the other, let me see how much time we have left here. Come on, go away. Put the light back on here. I think I found an example. Number 39 might be good if I've still got time. Number 39. Yeah, we might have enough time here. Let me try to wrap this video up here with number 39 from chapter 23. Because this one's about a charged conductor, and I think we could afford to have another example about those. That might be good. All right, so here it is. Number 39 from chapter 23. The only other problem I can think of in terms of problem types that I haven't worked yet is like you could have a uniform charge that's over a cylindrical shell. So we didn't quite work that, but I think the techniques that I've shown you will apply to solve that as well. But this is number 39, 23.39. My final example for today. The electric field at the surface of a charged solid copper sphere with radius 0.2 meters, all right, is 3,800 newtons per coulomb. All right. Directed towards the center of the sphere. All right. What is the potential at the center of the sphere? So let's put the center of the sphere at the origin. All right, let's make 0 the center of the sphere. So what's the voltage at 0? If we take the potential to be 0 infinitely far from the sphere. This is a great question. Oh, wait a minute, is that it? Hey, I'm gonna be out of here in no time, woohoo! All right, so how do we do this? So this is a conducting sphere. All right. And we know that the electric field is 3,800 newtons per coulomb right outside the surface, right? And it said it's directed inward as well, right? So if I was to draw some field lines, they look like this. They should be symmetric, right? They got to be, you know, everywhere around it. And they're directed inward, right? Everywhere there's inward pointing perpendicular to the sphere, right? Because it has to be, you can't have a parallel component to the electric field at the surface of a conductor. Otherwise it'd be pushing charge around on the surface. So they have to be perpendicular. And 3,800 newtons per coulomb, well, we can figure out the flux, right? What's the flux? So the flux here at the surface, right, would be, well, 4 pi, the radius squared, times the electric field, right? So we can work that out because we know the radius, we know the magnitude, right? And why is there electric field coming and into the sphere like that, right? Where is the charge? Well, there has to be negative charge at the edge of the sphere, right? There has to be negative charge like here. Boop, 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 bop, beep, bop, bop, bop. All right. So this has to be, this is, first of all, it's negative because it's pointing in, so minus that. And that's equal to the charge enclosed divided by epsilon naught. So therefore, the charge on the sphere is equal to, you know, minus 4 pi epsilon naught r squared times E. Let me work out what that is numerically. Just out of vain curiosity. I don't always find the numbers mid-problem, you know, but I'll do it this time. All right, so we've got 4 times the pi times I forget the epsilon. I'm going to use my calculator. Constant. Epsilon naught is 32 and my constants. So times 4 times pi times epsilon naught times r squared, which was 0.2, square that guy, and then still times 3,800. I get, that seems kind of puny, but minus 1.691 times 10 to the minus 8 coulombs. So that we could also write as Q equals to minus 16.91 nanocoulombs. So that's apparently the charge that's on the surface of the sphere, right? And so because this problem has spherical symmetry, it's the voltage, we can just write, it's the Coulomb potential. It's KQ over R. This makes the voltage 0 at infinity, right? And it also has a derivative which reproduces the electric field that we want. So this is whatever that is, which I probably shouldn't have calculated this because I could have just put, you know, 1 over 4 pi epsilon naught, right? That's K. And then my Q was minus 4 pi over epsilon naught, right? Minus 4 pi epsilon naught, R squared E. That would have been easier. There's my charge, and I got to divide by, well, divide by R, right? So, so that would be, is there something else in here? I'm almost done. So that would be the formula here, which would just be minus R squared E divided by little r. And great, but this is only for what? What's the context of this formula? This is for little r greater than 0.2 meters, right? This is only a legit formula outside of the conducting sphere, because inside the conducting sphere, there's no variability of the voltage. The voltage is constant, as I was talking about a second ago. So the voltage right outside, so the voltage is constant, so it should match the, I think it's supposed to match, yeah. Let's see here. So I believe the voltage we're looking for, because whatever the voltage is at the edge, it should be the voltage in the middle. So I think we just want to do basically, you know, KQ over the 0.2 meters, which I guess here would be KQ over R. So if I haven't messed something up, I think we can get it from you know, minus R squared E divided by big R, which is just going to be minus RE. So I think the voltage is just, let's see here. Well, that's not right. It should be negative. Oh, yes, it should. It's negative. It's a negative charge. I'm a dummy. I'll get it eventually. So 0.2 times 3,800. So I believe the voltage is minus 760 volts. That's the voltage that's constant throughout the sphere. Now the change in voltage is 0 throughout the sphere because it's electric field 0. Let's see, so that was number 39 of chapter 23. Let's see here. So what did we get? Minus 760 volts. Woohoo! All right, so it's done. It's over. Stick a fork in it. Have a good weekend, guys. I'm done. I'm out of here. See you guys Monday.